Afternoon, everyone. We're just going to give it a couple more moments and then we'll get started at the top of the hour. Thanks for calling in. Okay, everyone. I have 2 o'clock on my watch. Good afternoon, everyone, and welcome. Thank you for your patience as we open the room up and allowed a little time for folks to filter in here. And thank you all for attending this now third session of our 7-part webinar series. I'm Mike McGough, Executive Director with the National Corrugated Steel Pipe Association, and I will be one of your tour guides today on our journey this afternoon. Today we'll be discussing the installation practices, guidelines, and specifications for corrugated steel pipe, pipe arch, and structural plate. We will cover areas ranging from backfill design and foundation preparation to the placement, compaction, and backfill to post-construction inspection and the important considerations used during these steps. These webinars are being presented by the National Corrugated Steel Pipe Association in partnership with the American Galvanizers Association. Future webinars will be hosted every 2 weeks at the same bat time, same bat channel, 2 p.m. Eastern on Thursday afternoons. Future topics will cover areas such as detention and water quality, sustainability, quality and certification, and rehabilitation. PDH and learning units credits are available for those participating this afternoon. So please be sure to take advantage of this free opportunity. Membership of the NCSPA is comprised primarily of steel coil manufacturers, coaters, and fabricators. The mills or manufacturers will produce and coat the steel coil and then ship it to the various fabricating companies that will in turn roll form, rivet, or fabricate the steel into the various profiles for either pipe arches, or structural plate buried bridges that have been installed under our nation's highway system for over a century. As a quick review, on our first webinar, we discussed the types of coatings available for corrugated steel pipe. These coatings include galvanized or zinc-coated CSP, aluminized type 2, polymer laminated, and post-pipe fabrication applied coatings and pavings such as asphalt coating and concrete linings. In reviewing each of these coatings, we covered the material specifications that have been developed, the decades of research that have been conducted, and the types of protection they each provide. From the cathodic protection provided by zinc to the barrier coating of aluminized type 2 to the environmentally resilient polymer laminated coating resulting from the strong chemical and mechanical bonds developed during the laminating process. Of course, inherent within each of these coatings is its ability to perform in specific environments. Not all coatings are created equal. This table presents the expected service life for each of these coatings based upon the environments in which the products are installed. During our second session, we covered the structural design methodologies used to develop fill height tables for each standard diameter, gauge, and profile of corrugated steel pipe and pipe arch using both the AISI methodology and using AASHTO load resistance factor design calculations. Now, while there are seemingly countless options out there, the standard mechanical properties of the product allow for straightforward design calculations, resulting in fairly consistent fill height tables regardless of the methodology. Tweaking the knobs on the factors will have some effect on the tables. In most cases, the effect will be realized on the maximum allowable cover. However, the resulting maximums will nearly always exceed the maximum heights for competing products. This again is calculated by evaluating both the ring compression strength of the pipe, also known as the thrust, and by a pipe's ability to withstand the bending failure of the pipe wall. The thrust or ring compression is calculated by combining two factors, dead load and live load, then multiplying that combined load by the diameter and dividing by 2. Simple and straightforward, right? The soil structure interaction between the pipe and the backfill is different for flexible pipe and rigid pipe. Flexible pipe, as the system is compacted and as consolidation occurs, will deflect along with the soil, shedding some of the load, while rigid pipe will actually attract the load. The ratio of this interaction is illustrated here on this slide. For a given loading condition, a rigid pipe will likely have to be designed to carry approximately 3 times the load of a corrugated steel pipe. Now, why is it important to have bending strength if the pipe is just going to sit in the ground and be covered by dirt? Well, you have to move this thing around, right? And it's this resistance to flexure that is crucial when handling a pipe in the yard or on the job site. It also comes in handy during the backfilling process, most sensitively on larger structures. The structure just simply must have enough strength to resist the distortion. You don't want this thing to rack at all. This slide boils the procedure down into 7 simple, easy to follow steps. First is determining the pipe properties, i.e. the thickness and the profile. Then you're determining the thrust, the compressive stress acting on the pipe wall. And then you're determining the maximum allowable stress that can experience, either an axial or compression, an actual compression or ring compression, and then you have the flexibility factor to walk through. If it's a riveted pipe, you'll have to check the seam strength on it. You do a quick check for the minimum cover that's required. And then if it's a pipe arch, you need to look at the bearing pressures on the corners. So why is this important for today's discussion? Primarily because these structural design concepts are also applied during the installation process. As we said before, the pipe is completely backfilled and properly supported by the soil envelope. The pipe must have adequate bending strength to resist the shape distortion during handling and installation. As fill is placed against the pipe, the soil exerts active lateral pressure on it. Additionally, forces are applied to the pipe through backfill placement and compaction, so there's a certain minimum bending strength that is required to resist these forces. But once the backfill depth over the structure overcomes the active lateral pressure that the soil exerts, the structure becomes completely under ring compression. That depth of cover is typically span over 8, and that is often considered the minimum cover for normal live loads. Now, to go into more detail on this, with us today, we have my co-host here, Mark McCord with Southeast Culvert out of Winder, Georgia. Mark is a yellow jacket out of Georgia Tech, graduating with a civil and environmental engineering degree. He has over 18 years of experience in the drainage pipe manufacturing industry. He's been an active participant on NCSPA's Technical Advisory Committee for most of his career and he currently serves as the second vice president of the association. With that, Mark, I'm going to turn it over to you. Take it away.
All right, guys. Well, I appreciate it. Like Mike said, my name is Mark McCord with Southeast Culvert in beautiful Winder, Georgia. If you would like to know where Winder is, locate Athens, Georgia, where all the mouth breathers from the University of Georgia attend, and we're pretty much right there. So I will say today is my first time ever presenting directly to a computer screen, so we'll see how this goes. If it's terrible, you can go talk about it in the chat room. But we will be talking about installation and construction procedures for corrugated metal pipe. I'll go ahead and give you a list of references. Our technical references are AASHTO Section 26 and ASTM A798, standard practice for installing factory-made corrugated steel pipe for sewers and other applications. And then also our design manual from the NCSPA, Chapter 10, Installation and Construction Practices. This design manual is actually available on our website, which is ncspa.org. You can get a free download there, or you could go to one of your local manufacturers, and I'm sure they'd be happy to give you a hard copy if you're still into those. So let's move on and let's get into this a little bit. We want to talk about backfill design. We talked about this some 2 weeks ago when we looked at structural design, but like Mike mentioned, it's also very important for the actual installation of the pipe. Corrugated steel pipe is completely dependent on the backfill due to the soil structure interaction. Hold on, I'm going to see if I can move some stuff around. Like I said, this is my first try here. But every installation is pretty much unique. So you want to look at it and you want to determine the proper backfill for every single situation. And your backfill is actually defined by the soil stiffness or the quality of it. And that's a result of the composition of that soil and the level of compaction that you can get into it. Non-plastic sands and gravels are typically preferred. Are we having trouble hearing? Can everybody hear me? Okay. And a lot of times the native backfill on the site are acceptable as long as they're not organic. Most of the time I'll refer to the geotech to look at those and make sure that they are acceptable. When we get into higher fills and larger structures, it's pretty self-evident that your backfills need to be a little better, whether they're rock, gravel, whatever they may be. But normally a 90% standard Proctor is sufficient for your backfill compaction. When you're looking at AASHTO, normally A1, A24, A25, and A3 are acceptable. I don't claim to be a soil specialist, but this is how they really break it down. Like I said, when we're looking at native materials, I really fall back to the geotechnical engineer to evaluate them to see if they are acceptable. So the first thing that we really want to talk about is location and excavation. And we really look at two types of conditions when you're installing pipe. You have your embankment condition, which is where you're essentially setting the pipe onto the natural ground and backfilling it from there. And then trench conditions, which is, a trench where you're digging a hole and you have walls to compact against. And those are where you really need to be conscious of the shape and the width of your trench while you're going into your installation. Base preparation. This is very important, grasshopper. Like everything else in life, you have to have a good foundation. They allow for uniform grade, shape, and load distribution of the pipe as you begin your backfill preparation. So there are really two types of foundations that we really consider right off the bat. They are soft foundations and rock foundations. Soft foundations will cause settling and uneven settling of the installation. So you really want to over excavate those foundations and replace them with good fill. And then rock foundations, they cause concentrated loads and distortions of the pipe because you get those hard places in the soil. again, you want to over excavate that foundation and replace it. Down here where we are in Georgia, we will typically see a rock base on our foundations just so you have a good solid foundation to seed into so that you can begin your installation. Sorry, one other thing I wanted to mention is you do get the occasional situation where you have a transition between the two. When you do get that, you want to take special care to make sure that you have uniform support across there, because you could get some differential settling in the pipe due to the rock in the saw. So let's just talk about normal bedding of a round pipe. So the portion of the foundation that is in contact with the bottom of the structure, we refer to as bedding. The bedding can either be flat or shaped. Good bedding foundations can be viewed as a cushion for the pipe and should be relatively yielding when compared to the compacted material that's going to be placed between the trench wall or the embankment and the pipe. And in this manner, the soil arch can develop over the pipe, which reduces the load transmitted to the pipe itself. With flat bedding, which is pretty typical for factory-made round pipe, the pipe will be placed directly onto the fine-graded upper portion of the foundation. And then the soil is compacted underneath the haunches of the structure in the first stages of backfill. We refer to the haunches as basically the area from halfway up the pipe down. So the upper 2 to 6 inch layers of your foundation should be pretty loose. That allows your corrugations to seed into the bedding. Moving on, let's talk about pipe arch and large diameter foundations. We kind of group these together because the bottoms of these structures are fairly flat, so you can kind of talk about them in the same conversation. But in these situations, the bedding should be shaped to the approximate contour of the bottom portion of the pipe. Alternately, the bedding could be graded into a V shape. Shaping this bedding affords a more uniform support to the flat bottom of these types of structures. The soil beside and below the corners of the arch must be of very, very high quality and thick enough to spread and accommodate the high reaction pressures that develop at those locations. It's important in pipe arch installations to ensure favorable relative movement of the haunches with respect to the pipe bottom. A slight yielding foundation under the bottom as compared to the haunches is really desirable. And one more note when you're looking at these, because a lot of times with larger pipes, you're seeing them installed into wet applications, whether it be a stream or whatever. Most backfill operations are conducted dry, but you will run into the rare case where they are conducted in wet or submerged conditions. In these types of situations, a good quality granular backfill that really achieves its required strength when it's dumped into standing water should be specified, because you're obviously not going to get compaction in that soil if you've got heavy water. All right, I am not going to touch a whole lot on camber, but it's worth noting when you're talking about the foundation. Camber is really where you just build up the foundation because you expect settling under high fields or an embankment. It's really just an increase in the foundation elevation at the center of the culvert above a straight line connecting its ends. And this really helps you to prevent sag in the pipe, where you could potentially get standing water or sedimentation after that center would settle. So here, before we get into the actual backfill operations, let's talk about some pretty common sense things that go with installation of the pipe. With unloading and handling, I mean, it's straightforward. You don't want to dump the pipe off the truck. You don't want to be dragging it across the job site. Just use common sense and reasonable care. That way you're not beating the pipe up before it even gets into the trench. Coupling is very important. Proper joints will eliminate infiltration and exfiltration, which will really cause problems in the future with the backfill surrounding the pipe if you have those problems. You can go in and actually add a gasket or a geotextile wrap that will prevent soil infiltration and exfiltration. When we're dealing with smaller pipe installations, we'll typically supply one-piece bands. With larger pipes, we'll give you two pieces that can be bolted together. Our most making sure we're not having audio problems here. So, all right, good to go. Our most common type of band here is our hugger type band. And I would say that the majority of the manufacturers in the country are probably supplying those for the reformed ends that we manufacture. So let's really get into the placement and the compaction of the backfill. Like we mentioned earlier, flexible structures are completely dependent on the backfill for the structural integrity. And so backfill selection and compaction are critical for proper installation. Like we mentioned, native soils are typically acceptable for smaller structures, but when you get into bigger structures, you really want to start looking at a better backfill material. I try to keep my opinions out of these things as much as possible, but really, when I start to get up into the 5 foot, 6 foot diameter pipes, is when I'm really going to start thinking about a finer granular or stone backfill to make sure that those haunches are truly supported when you get into installation. Like I mentioned, larger structures and higher fills are going to require more care, and that's when you really want to start thinking about a granular backfill. And then backfill for all structures should be compacted to a specified 90% minimum per AASHTO T99. So let's get into talking a little bit about equipment. I'll talk a little bit more about this later. But equipment plays a big role in the actual installation of the pipe. When you're doing the haunches, you're going to want to use hand equipment because that's really one of the most important areas of the installation. It's tight under there. It's hard to get to. So your mechanical compactors are not going to work. Your rollers are not going to work. Once you get up to about the spring line, you can start bringing in your mechanical compactors. You just want to make sure that you're not banging up against the structure and damaging it. Rollers can be used. I really like to see the rollers once we probably get up over the pipe. Like your walk behinds, I don't want to see any of the larger ones there, but walk behinds are fine. And then you got vibrating compactors, which are really good for granular material, essentially settling out your stone, but you don't want to really use those on any type of clay or plastic soils. So placement and compaction of backfill. Like I mentioned a minute ago, the material under the haunches has to be in firm contact with the entire bottom surface of the structure. The haunches are the most difficult to backfill and compact, and sometimes don't receive adequate attention during the process. So care must be taken to eliminate voids and the soft spots in those places. Place the backfill equally on each side, pretty much in uncompacted 6-inch to 12-inch layers. And then each of those layers has to be compacted to the specified density before the next layer can be added. Those compacted layers really need to extend to the trench wall or to the compacted embankment material. The backfill immediately next to the pipe should be compacted by hand-operated methods. Heavy compaction machinery may be used as close as 3 to 6 feet, depending on the size of the pipe. But when you're doing that, you really need to pay attention to the dimensions of the structure, because if you start seeing dimension change, that equipment is way too close. You need to move it away. And then select material really less than 3 inches require less compaction and effort for lift thickness. So a lot of times down in your haunch material, haunch area, those are going to be the good choice. And then all your equipment has to be run parallel to the length of the pipe until the backfill reaches at least 3/4 of the rise of the structure. So I'm going to talk a little bit about this, but if you want to hear more about multiple barrel installation, come back in 2 weeks and we'll talk more about it. But a lot of times you are putting in multiple barrels, a lot of times in streams, like you see in the pictures, underground detention systems, where you're putting barrels side by side. So it kind of changes your dynamic because you don't necessarily have the trench wall. You have to get spacing correct and everything like that. So your spacing really must be adequate for proper backfill placement, haunching, and compaction. And the minimum spacing depends on the shape and the size of the structure, as well as the backfill material. Kind of one of the old rules of thumb for spacing is basically half a pipe diameter is good spacing. So if you were installing a 72-inch pipe or two 72-inch pipes, you would want to have them about 3 feet apart. But that spacing can be reduced somewhat if you're using crushed rock or other backfill materials that are used that can easily flow into the haunch and don't require a whole lot of compaction. That spacing can actually be reduced down to 18 inches, potentially less, depending on what you're using. So if you're using controlled low strength material or CLSM as backfill, then the spacing is restricted to that necessary to place the grout between the structures. So backfilling between and outside of the structures must proceed at the same time so that you get a balanced load down the pipe. You don't want it racking either way. And the room required for the desired compaction equipment really plays a big part in this because if you got them too close together and you're using a big piece of machinery, it's not going to work out very well for you. So like I mentioned, in 2 weeks from now, we are going to do a webinar hosted by myself and Daryl Sanders from Contech, as well as Mike McGuff, on detention and water quality structures. And we'll see more of this multiple barrel installation in that webinar. So let's just talk about a couple of little special considerations during backfill. Hydraulic protection during backfill is very important. If you've never seen a pipe that's been installed and then overnight you get a really heavy rain that you weren't prepared for, it's an interesting sight. Typically that pipe goes from a horizontal installation to a vertical installation very quickly. So like I say, a lot of times this water kind of goes where it wants to go. So prior to the completion of your backfill, your permanent end treatment or slope protection, the pipe is vulnerable to flow conditions that are going to be different from your final condition. So examples of these are flow on your unprotected ends, unbalanced load, loss of backfill, uplift forces. All of these are going to require some type of temporary protection on the ends. So placement of your end treatment and slope protection as early as possible are very, very important. And so if you go in at the beginning and you actually place your head walls prior to backfill, you want to start at your head walls and backfill towards the middle. If you install your head walls or end protection at the end, you want to start at the middle and move out. So a couple of other things to talk about. Construction loads are very, very important. It's something that a lot of contractors don't think about until it's too late. But construction loads are different from your final loads just because you've got very heavy equipment, essentially with no pavement to distribute your loading. So you need to make sure that during the construction process, you have got the minimum cover, at least the minimum cover, allowable for that construction equipment to be on top of the pipe. And then another situation is to know what your minimum cover is. For most pipes, it's going to be in the 1 foot ballpark, but know what that is, so because that's going to be very important. Excuse me. But then shape control is also very important. You want to watch for peaking or rolling. Peaking is where you backfill on the side, so your pipe tends to push towards the push up vertically, or rolling is where it tends to rack towards one side. Vertical deflection during installation is pretty much expected. The sides of the pipe are going to move out, your top's going to move down. With good practice, this really shouldn't exceed probably 2% of the rise. Pipe arch, a large portion of the vertical load over that pipe is going to be transmitted into the soil at the corners. So the backfill at the corners must be able to provide at least 4,000 PSF of bearing resistance. And then we already talked about multiple barrels and the adequate spacing. But end treatments are, like I mentioned, are very important as well. Those include bevels, skews, flared ends, head walls. They really need to be considered during the backfill process, because if you're using like a bevel or skew, for instance, you're cutting that pipe, so you're taking the structural integrity out of the pipe. Those have to be reinforced to prevent any type of damage. So all of that really said, construction supervision and control is the key to all this. As long as you're paying attention and using common sense, you shouldn't really have any issues. Just a couple of pictures of some of the end treatments that we have out there that are available. Prefabricated head walls. You see some retaining walls and some rock walls, some gabion baskets. We have a wide variety of end treatments that we can use here. The one in the middle there, that's kind of what I just mentioned with our bevels and skews. Right there, you can see a bevel with a slope collar used for reinforcement. That just prevents any type of damage on that end, keeps it in shape once it's finalized. A couple of more pictures for you there. You've got multiple flared end sections on some arch pipe, and you can see how little cover is actually on top of that pipe. And then we've got some unfinished bevel pipe there. So let's just kind of look at a summary of what we've gone through here. One, use good backfill material. That's pretty common sense. And ensure good backfill and adequate compaction underneath your haunches. Maintain an adequate width of backfill for your embankment conditions. That's about 1 pipe diameter. For trench installations, it's going to be to the trench walls. Place your material in thin, uniform layers and balance those layers as you proceed down the pipe. Compact each layer before adding the next layer, and then monitor the design shape and modify as needed. And then again, don't allow heavy equipment over the structure without adequate cover. That, like I mentioned before, that when a contractor can't see it, that's where you can really get in trouble. So you want to make sure that they're aware of that up front. So most entities now actually require some type of post-construction inspection. For round pipe and single radius arch deflection criteria, basically less than 7.5% of the manufacturing tolerance is acceptable. For ellipses and pipe arches, low and high profile arches, 10% of the design radius is acceptable. And what you'll see is really 2 types of inspection called for: video inspection and direct measurement. Most of the video inspections you will see on small diameters that you can't get into. Once the pipe gets large enough that you can actually get into it and access it, you'll see direct measurement come into play. Typically, that's either in the 48 to 54 inch ballpark. So during post installation, a couple of things that you actually want to look for. You want to look at your gaps in your pipe, in your bands. Anything over 1 inch, you probably want to look at that and remediate it. You also want to look for soil infiltration and exfiltration. Like we mentioned earlier, if you have that, that's going to cause trouble down the road, because you're going to get loss of compaction in the soil that surrounds the pipe. So if you do find that in a band or a joint, you want to remediate that. You also want to note any type of buckling or bulging, or like any point loads in that structure, and really just make note of it. Make sure it's not growing. And then notice the deflection limits. At 5%, you probably want to take that and you want to bring it to the engineer and evaluate it. Greater than 7.5%, you're going to need to replace that structure because you're exceeding your limits. You also want to note any coating problems and repair those. This really applies to, let's say, polymer coated more than anything. Polymer coated during the construction process can tend to get scratches in that coating. If you find that, what you want to do is repair it by the manufacturer's recommendations. You can either paint it, you can tape it, whatever, but you want to make sure that you do that in order to protect the coating moving forward. So like I mentioned earlier, you can go onto our website and really you can get all this stuff for free. It's ncspa.org. The download is for the manual is free there. And guys, check out the website because you can also find all of the webinars that we have going forward. I think we have 4 left. So I am going to turn it back over to Mike McGough right now, and he is going to take us home. And like I said, I appreciate you guys being here. I thank you for your attendance, and have a wonderful day.
Thank you, Mark. I'm going to scroll back here just a little bit to cover a couple more things on the website. So as Mark said, yes, registration is available. The webinars that we've done already will be posted on the website eventually. I think the first 2 are up now. We will be uploading the rest at some point, certainly in the near future. Quick access to the calculators are available through these 6 links down here. If you want to download the copy of the design manual, of course, that's accessible here. And of course, the top line, information on products, applications, technical resources are all available here. Information on our quality and certification program are here. Public policy and advocate is listed on this part here. And then, any news or events, if you want to find a project, that's all located under the newsroom. So moving on, 2 diagrams here, very similar to what we presented before. These are taken straight from AASHTO A798. And what they show here are the 2 types of installations, a typical embankment installation and a typical trench installation. Just a couple of things to point out for consistency's sake. You're looking here at that minimum cover, D over 8 or span over 8 or 12 inches, the greater of the 2. Same thing here, whether it's an embankment or trench installation. Here we talk about lifts, 6 inches to 12-inch lifts during compaction. A large rock here is indicated in trench installation must be at least 4 feet above the pipe itself. So this eliminates the choice or the chance of any point loading on the structure. So now how does that go from 798 to standard drawings for DOTs, right? So here, this is an excerpt from North Carolina. This is their standard detail for flexible pipe. This is in particular the trench installation. So again, just to highlight a couple of things here. This is the loosely placed select material underneath as the bedding material. Illustrating again here to take care to fully compact the haunch zone for the pipe backfill. And then backfill material is here as a class 3 or a class 2, all the way up above the spring line into, is there a level here? Somewhere above the top of the pipe. Again, this is in a trench foundation, and then this is a pipe above ground. So again, an embankment. Again, very similar conditions. Just to kind of make everyone aware of one state's example as we've been doing. Now, more information certainly is available on the website. As we've talked about a couple of times already, we have the design manual available, but in particular, one last thing really to point out is the installation manual. So this covers steel pipe and structural plate. Basic considerations, it breaks it down into, an 11-part procedure. You can run through that here. I'm not going to go through it again. This is available as a free download from the NCSPA website. If you go under technical resources, you can find it there. Again, there are a number of projects available for you to review and look at, different applications, different installations, different project sites and conditions. If you go to the newsroom, again, find a project, each one of these bubbles will pop up a pretty good story with some pictures and a link to, you know, the company that actually produced the project. With that, gang, we can wrap things up. You can follow us, of course, on social media, at the NCSPA on Facebook, at NCSPA at LinkedIn, at Corrugated Steel on Twitter, and at the NCSPA on Instagram. Again, as Mark talked about before, detention and water quality will be our next webinar in a couple of weeks. If you haven't already, please register and tune on in. And with that, we'll wrap things up, and happy to answer any questions that might be out there. Yes, Jim, thank you for that correction. A798 is an ASTM specification, not an AASHTO specification. Thank you for that clarification. All right, well, thanks, everyone. Take care of yourselves, and have a great rest of your day. Oh, across the country, how often do you run into issues with chemical reactivity in soils that affect the longevity of installations? Yes, that's an excellent question. So I think you're alluding to maybe the use of chemicals, de-icing salts above the roadway. So the best place I can point to you is we just developed a TechNote 210. You can download that from our website, and that goes through some installation practices to mitigate what happens there. So again, it's TechNote 210 from our website. You know, in essence, what you're talking about are a couple things. One, you know, if you're going to use a metallized coating, would be the use of a geomembrane over top of the pipe or the structure to shed those chemicals away, or a polymer coated pipe would also serve that same purpose. So if there's any other questions, thanks again for the time, everybody. Be safe and take care.